VLSos here. This is a video lesson on variation forms. There are two forms of variation that we'll be talking about. And to get a general idea, I'm going to sketch a graph. And imagine that we have a function that increases. It's not necessarily linear. It could be. But the idea is that f is always getting larger. As x increases, the value of the function increases. And another general trend or variation that we could compare it to is another function we'll call g. It could be linear, but not necessarily. So I've shown that it does some curving. But g is going down. It's always decreasing. As x increases, the values of g are always going down. To spell out the difference between f and g, let's focus on this idea of the variables changing. F shows a general function that has the quality that as x increases, y increases. And if we could imagine moving in the backwards direction along f, in other words, if we decrease x, then likewise y will also decrease. That there's a relationship between the variables and how they vary that is the same. X increases, y also increases. X decreases, y also decreases. This is what we call direct variation. And if direct variation was all that we knew about the function, then we could capture the idea of direct variation quite simply in an equation, y is equal to k times x. And this means that we have an equation, and the only thing that we know about it is the relationship between the variables x and y. As one increases, the other increases. And as one decreases, the other will also, based on this fundamental mathematics. G is an example of the other kind of variation. In G, as x increases, y decreases, and vice versa. If y increases, then we must be decreasing x on g. So they're different. The variables, if you know one, you know that the other is going to be the opposite of it. And we call this inverse variation. And the fundamental mathematics, if we were to write what we knew about the equation, if we only knew that it had inverse variation, would allow us to create this equation form, y is equal to k divided by x, because that captures mathematically the relationship between the variables in inverse variation. Increase y, x must be decreasing. Decrease y, x must be increasing. K that shows up in the structure of these two fundamental forms of variation is what we call the constant of variation. It's not a variable in itself. We could call it a parameter. And if we were to have a problem and knew the variation, then we would need more information in order to be more complete in what the equation is. For example, we could be told that y varies inversely with the square of x. and contains the point 3, 1. If this is what we know about the equation, how it varies, and a little bit more, one specific point to help us, then we are able to write the general form of the equation and then use that point to complete it. This is inverse variation, and so the general form is going to be y is equal to k over x, but not just x, literally the square of x. So we can write or start with the equation y is equal to k over x squared. This is the beginning. Now if I have a point 3, 1, I have an x and y value to work with in order to then solve for the unknown k, the constant of variation. If I put 1 in for y when x is 3, I can create an equation with k unknown. I'm going to square 3 to make 9, and if I multiply both sides by 9, I can see that k will equal 9, which allows me then to complete the equation y is equal to 9 over x squared. Very often when we are observing the relationships between concepts and quantities in the real world, one thing that we can get a sense of in discovering a new way that our environment and our world works is how the quantities vary according to each other. Starting with the concept of variation, we can then take measurements in science to get some data which allows us to build a model, and the model would then be a mathematical equation or a relationship between the things that we were measuring and studying. Often, understanding how quantities vary is the beginning of a greater understanding. It allows us to then think of the fundamental nature of the model that we're trying to discover and produce.